So good morning, everyone. I just have a few announcements to make. Don't forget, next week, Monday, we have a midterm. Very important. After the lecture, so please don't miss the lecture because that's very important as well. So we'll have the lecture and at 11 o'clock is the midterm. And it's on lectures 1 through 3, so including today's lecture on thermodynamics and the first 3 tasks, including today, what we're going to do today, water. And I've posted the videos on YouTube for your convenience, under my channel. Right, so you can look at them. And basically, these are 2-hour lectures, so there's basically I've broken it down. There'll be 6 lectures, but it's basically lectures 1 through 3. Does everyone understand? Does everyone? Any questions? Okay. So have fun with Fabrice today, and see you later.
Okay, so today thermodynamics, we're doing some physical chemistry. So when we do chemistry, generally there are 3 questions we want to answer. And the first 2 are, is my reaction going to happen? Am I going to spend hours and hours in the lab and then nothing's going to happen? And the second one is, how much energy do I need to put into my reaction, or how much energy am I going to get out of my reaction? If I need to put the same energy that's in the sun to get my reaction going, I'm not going to do that, because I can't do it. And if I get the same energy as the thermonuclear bomb when I make the reaction, I'm not going to do that either, because I don't want to kill people. The third question is, how long is it going to last? Because maybe I can answer that's fine for the first 2 questions, and the last question is going to tell me, well, it's going to take 1 million years to achieve your reaction. So I'm probably not going to start either. So the first 2 questions are answered by thermodynamics, and the third question is answered by kinetics. So kinetics we'll do next week, and thermodynamics we're going to do today. So thermodynamics, it comes from Greek. And therme means heat and energy, and dynamics means the study of how things move. So therefore we're going to study how energy moves from one system to another system. And that helps us making predictions on whether my reaction is going to happen or not. So we need to start with doing some conventions. So I don't know if you've seen that at school before, but it's always good to remember. So the system, when I talk about the system in a lecture, is what you want to study, what you're interested in. Everything around the system is called the surroundings, and the universe is the system plus the surroundings. Okay? Now, it's very important how you define your system and your surroundings and your universe. For example, you can have a beaker as your system, the air in the lab as your surroundings, and the universe is the lab with the beaker inside it. Okay? But I could also define my system as the molecules inside my beaker, the surroundings as the solvent, and the universe is just the beaker. Okay? So you're going to get different answers depending how you define your system and your surroundings. So it's always important to define your system and surroundings first. So we can have different kinds of systems. The first one is an open system, and in an open system you can exchange matter and energy with the surroundings. So the example is a cup of coffee. The heat goes out from the coffee into the air, and you can split it, and you lose matter. Okay? You can have a closed system. In a closed system you can exchange energy, but not matter. So that's a closed cup of coffee. You're unlikely to spill it, but you can still exchange heat with the surroundings. And the last one is an isolated system. And in an isolated system, you cannot exchange anything, no matter no energy. So that's your thermos flask. Okay? So in thermodynamics, we are interested in what we call the energy process. Okay? So you can exchange energy in terms of work and in terms of heat. Okay? So work is normally defined as W, and heat is called Q. Okay, these are the symbols we use to define work and heat. And these are both transfers of energy. Okay, they are not work and heat are not forms of energy. They are a process that is a transfer of energy. Okay, that's what's important to get that. So the SI units of energy are joules. Okay, and sometimes you can find energy reported in calories, like on your food. And 1 calorie is 4.184 joules. Okay. Now I will never ever stress enough that units are your friends. If you can work out your units, you can work out everything. Okay, so and a number without units is a number that means nothing. Okay, if you hand me your tutorial next week and you write no units, I'll probably write after sausages, potatoes, it can be anything. The number can mean anything. Okay, so you must have units all the time. So let's start with work. Let's think about this reaction here. You get the zinc and you put it in reaction with hydrochloric acid. Okay? What's going to happen is that you're going to create hydrogen gas and zinc chloride salt. Now what happens if I put a balloon on top of my flask is that the gas is going to go out and it's going to start inflating the balloon. Okay? And that is doing work. The system is doing work because the gas that's expanding the balloon expands against the atmospheric pressure. Yeah? So therefore it has to do some work to expand. Think about it, if you blow into a balloon, you have to do quite a lot of work at the beginning because it's difficult to break the balloon. Yeah? It's the same. And because you're doing work, you're releasing energy into the surroundings. Okay? So, so the surroundings is now the balloon and the atmospheric pressure, and the system is doing work. So if you think about the balloon expanding, it tends to expand outwards in a nice, smooth motion. Yeah? And work is a transfer of energy that is quite uniform. So if you think about work, everything works into one direction. Okay? If you think about heat, on the other hand, heat is the random motion of molecules. Yeah? And therefore it's going to go in every single direction. So the difference between work and heat is that work is a uniform motion in one direction, and heat is a random motion in all possible directions. Okay? So heat is messy, work is quite rigid and nice. Does that make sense? Yeah? So when my balloon is inflating, the energy leaves the system to inflate the balloon and goes into the surroundings. So if you say that it takes 100 joules to inflate the balloon, the system has lost 100 joules because the energy has gone from the system to the surroundings. And because we always think in terms of the system, because it lost 100 joules, we say the work done by the system is minus 100 joules. Okay? So the convention is that if energy is leaving the system, it's a negative number. If energy is going into the system, it's a positive number, always. Okay? It's the convention in probably 99% of the books. If you do lots of reading, you might find that other people define it the other way. You just have to go with them. But in 99% of the books, and the book you have for this course is defined this way. Okay? But there are some people who don't agree with that kind of thought. It's a convention. Okay? It's just the way that people define it. So, how do we measure work? So, lots of reactions produce gas, so therefore it's important to know about expansion work. So the formula for expansion work is this. Don't be afraid, it's okay. So W is work. Px is the external pressure. So you work against the external pressure, generally the atmospheric pressure. dV is the change in volume in your system. Okay, so it's a small, so if you had delta V, that's a large change, dV is a small change. And that here is the integral. Do you all know about integrals? Yeah? Okay, no you don't. Okay, that's fine. So the integral is like doing the sum of all the small change of volume against that pressure. Okay? So there are formulas to work out the integrals, but basically you do the sum of all the small change between the initial volume to the final volume. Okay? That, and it's minus, because generally expansion work means that energy leaves the system. So that is the general formula for expansion work. So let's take different cases. Case number one. There's no force, there's no pressure against your system. Okay? So if P is 0, 0 multiplied by something is still 0, the work is going to be 0. Yeah? So if you have no opposing force, no opposing pressure, there's no work being done. It's like expanding in the vacuum. Okay? That's the easy one. Case number 2. You are expanding against a constant pressure. So there's a bit of math. So we know that W is minus dx dV dI and dF. Okay? So because the external pressure is constant, we can take it out of the integral. That's a rule of the integral. So we can write that as minus dx integral of dV dI and dF. And now that's easy because that is just the sum of all the different volumes. So all we're going to be left with is minus dx, and that's going to be dx minus vi. That's all the volume between vi and df. Okay, that I can write as delta V, and that's the result, minus dx delta V. Okay. So if your system expands against a constant pressure, that is the formula you use. W equals minus px at V. Now, all pressure is not, the pressure is not always constant. As long as your gas expands, if you think about the gas in the volume, in a balloon, for the balloon to expand, the pressure inside the balloon has to be greater than the pressure outside. Yeah? As soon as the pressure outside is greater than the pressure inside the balloon, the pressure outside will crush the balloon. Yeah? So the maximum work you're going to get is when the pressure inside the balloon is the same as the pressure outside. That's going to be your maximum work. Now this formula here, PV equals nRT, is a very important one. That's basically tells us everything about how gases work. So let's talk about this one for a minute. So this relationship is called the gas law, the perfect gas law. P is the pressure, V is the volume, N is the number of moles, R is the gas constant, and T is the temperature. Okay? So remember, units are your friend. You always use SI unit. So the SI unit for pressure, that's in pascals. Volume is in cubic meters. Number of moles is in moles. Temperature is in Kelvin, always. You know what Kelvin is? Yeah? And that leaves us R, our gas constant, and R 8.314 joules per Kelvin per mole. Okay? You will tell me I got Kelvin, I got mole, but I don't have any joules. But pressure times volume is in joules. Okay? Alright. So we have our relationship here, so we know how pressure and volume work together. Now what we have is we don't have a constant pressure outside our balloon, but we know that the pressure inside the balloon is the same as the pressure outside because we want to get the maximum work. So we know that W equal to minus Px V equal to R and Vf. And we know that Px is equal to P inside the balloon. Now we can rearrange this. So if I arrange that, I get that P is equal to nRT divided by the volume. I can put that in there. So I'm going to get minus VI and Vs of nRT over V dV. So my number of moles is not changing. R is a constant, and we're assuming that we're working at a constant temperature. Temperature is not changing. So all that is constant. The rule of the integrals is that the constant, we can take it out. So that's going to be equal to minus nRT integral of dV over V, VRA, and Vf. Yeah?
So why is that a constant?
Number of moles, I'm working with a set
Oh.
number of moles.
Okay.
Yeah, I'm working at room temperature.
Oh.
That's it. Now the integral of 1 over v is a log. Okay. If you don't know about integrals, you just need to learn this rules. So that's equal to minus nRT. That's going to be log of v between vi and vf. Okay. T, log of the F minus log of the I. And the property of logs, that's log of AB is log of A plus log of B, and log of A over B is log A minus log B. Okay, so I got that, I can arrange that there. I'm getting minus NRT log of yeah, over B. Okay. So that is the maximum work you can get out of your system if you're just expanding gas. So go back to there. And on the slide, that's what I've done. I've done the same thing. I've expanded my integral and everything, and I've got the same result. Okay. So it's on the slide as well. Yeah.
When I did this in high school, like the R, wasn't it 0.072, something like that?
Was that, did you use calories instead of joules?
Yeah, I think so.
Yeah, that's different because it's in joules. If it's in calories, that's probably your number there.
And can we also do it like the other way?
I would use that. Okay, for everything we're going to do here, I would always use that because joules is an SI unit. Okay, the calories is not SI unit. So always work in SI unit and you won't get any problem. Okay. Any other questions? Okay. So we know we can measure work. Now we have to measure heat. So for a specified energy, when it's also with heat, you're going to get a change in temperature. Yeah? You know that if you talk about heat, there's going to be a change in temperature in your system. And that depends on the heat capacity of your system. So the heat capacity is how much energy through heat can your system take or give. Okay? So the heat capacity is defined as C, and it's the heat divided by the change in temperature. Okay? So therefore, we know that Q is in joules, and we know that change in temperature is going to be in Kelvin. Therefore, the heat capacity is expressed as joules per Kelvin. Or heat, Q, is equal to the heat capacity times the change in temperature. That's going to be in joules. Okay. So the heat capacity depends on the amount of the substance in the sample. If you have 100 grams of water, it has 100 times more heat capacity than 1 gram of water. Okay? So therefore, generally heat capacities are reported per mass or per mole. Okay? So you get the molar heat capacity, which is your heat capacity divided by the number of moles in your system, and that's going to be joules per Kelvin per mole. Or the specific heat capacity, where it's the heat capacity divided by the mass of your system or your sample, as joules per Kelvin per gram. In chemistry, we know where you work with this one. Okay? So the molar heat capacity is the one that you find reported in tables. The nice thing is that people have spent lots of time and they have all worked out all the heat capacities for all the different substances. There are tables and tables and tables of heat capacities. Okay? which is good for us because then we can work out Q. Yeah. So if you have a large heat capacity, that means that your substance can absorb a lot of energy, okay, without raising its temperature too much. So if we think about it, if you transfer a certain amount of heat, but the temperature change is 0, then you're going to get an infinite heat capacity. Yeah? Makes sense. If you divide by 0, you get infinity. So, when do you think you're going to get a heat transfer, but no change in temperature? At which point? What do you think? When do you add more and more energy, and then there's no change in temperature in real life? Okay? So, like what? Yeah. At the boiling point, if you put your water on the stove to cook your pasta, you're gonna put heat in. Water is going to start changing temperature. Let's say which is 100 degrees C. At 100 degrees C, it goes into vapor, but the temperature of the water stays at 100 degrees C. You can input as much energy as you want, it's still going to be 100 degrees C. Yeah? So when you change physical states, your heat capacity becomes infinite. So away from these phase changes, generally it's fair to consider that your heat capacity is constant. So here what I've done is I've taken some data from the NIST website, and I worked out the change of heat capacity of iodine with temperature. Okay? So here is for solid iodine. You can see it goes from 57 to 60. We'll go from 350 to 400 Kelvin. That's not changing much, only 3 joules per Kelvin per mole. Then my heat capacity becomes infinite. That's a huge jump. Okay? And then I go into liquid state, and that's 80. It stays at 80. Okay? Then I change to gas, and once again it goes to infinity. And then once I've finished, I vaporize everything. The heat capacity of iodine vapor stays at 37-ish. Okay? So if you go away from those points here, when your heat capacity is infinite, it's normally constant. Okay? So in chemistry we know we work with one phase. Okay? So likely you're gonna heat your iodine from 350 to 500 Kelvin. Yeah? So therefore we can assume that your heat capacity within the temperature change we're going to study is going to be constant. Okay? Now, because of the graph, we know it's not true, it's not really exactly constant. But a change in 3 joules per Kelvin per mole is not significant to call it non-constant. Okay? So we approximate it to be constant. Okay? Okay, so we know the work and we know the heat. Now, what we want to know is the internal energy of our system. Now, the internal energy is the sum of all the energies in our system. So you can get kinetic energy, potential energy, everything into the system. In each atom, each bond, everything added together, and your system has its own internal energy. Because it's a sum of everything in your system, each atom, each electron, each bond, everything, it's impossible to know the internal energy of a system. Okay? However, we can work out the change in internal energy, because we know that we start with something, and then we add work and heat, and we end up with something else. Yeah? So we can work out the change in internal energy which is by adding work or heat, or making the system work, or changing the temperature in the system. And therefore, the change in internal energy, delta U, is equal to Q plus W. Okay? So we don't know U initial and U final, but we know the difference between the two, which is the change in heat and the change in work. So the system is literally blind to how you add energy to it. It doesn't matter. We just know that it changes energy. Internal energy is what we call a state function. Therefore, its value only depends on the initial and final state. That means if you have an initial state and a final state, you can take any route in between. You can add work this way or work the other way. It doesn't matter. You're going to get the same answer. Okay, that's what is a state function. And that brings us to the first law of thermodynamics. If your system is isolated, then there is no work being done and no heat transfer. So the change in internal energy is zero. Okay? The internal energy of an isolated system is constant. That is the first law of thermodynamics. So what isolated systems do you know? Give me some isolated systems. Sorry? The thermostat, yeah, the one I gave you earlier. Anything else? How about the universe? Our universe. Take all the stars and everything in the universe. It's a closed system. Yeah? Therefore, in the whole universe, it's isolated, and no energy is added, and no energy is lost. Yeah? So in the whole universe, the energy is constant.
So this is the law of conservation of energy.
The law of?
The law of conservation of energy.
Yeah, it's the same. It's the first law of thermodynamics. Okay? So in the universe, no energy is created, no energy is lost. It's already there. Always transformed. Now this is my interpretation of the first law of thermodynamics. I like my regards. Okay? So if you think of a room that is closed, okay? And you put a nice jigsaw puzzle with a nice log on the jigsaw puzzle in the room, and in that room you're going to put an angry cat. The angry cat is going to go in and it's going to destroy the jigsaw puzzle you just made. Yeah? Now if you think that the jigsaw puzzle represents the energy in that room, and the cat is just all the chemical reactions that happen. Okay? So it's going to scatter all the jigsaw pieces all around the room. They're going to be under the carpet, above the wardrobe, behind things, but it's still going to be there. No energy is lost, no energy is created, because the cat is not going to create a new piece for your jigsaw puzzle. Let's face it. Yeah? It might poop somewhere, but it will not create a new jigsaw puzzle piece. So therefore, all the energy is going to be there. It might be hidden, but it's going to be there. Okay? And that's my take on the first law of thermodynamics. That's the angry cat. The angry cat will return later on. So, we know that the total energy of an isolated system is conserved. It doesn't change. So these are other ways of expressing the first law of thermodynamics. So the energy lost by the system is gained by the surroundings and vice versa. The energy exchange can be in the form of heat transfer or work or both. And in an isolated system, the internal energy is constant. So if someone asks you what is the first law of thermodynamics. You can say it as, in an isolated system, the internal energy is constant, or you can write it as delta U equals Q plus W. Okay, so one is the mathematical form, one is the written form. They are both valid. So, if we keep our system at a constant volume, we're not changing the volume, we're making things happen, but the volume stays constant. So we know that the work is minus px dv. We know that that doesn't change, so that's going to be 0. Okay? So work is going to be 0. That's always handy because we don't like integrals really. So if the system cannot do any kind of work, then delta U is only equal to Q. Yeah? And because we want to remember that we're working at constant volume, we're going to put a little v next to Q. You see that's a constant volume. Yeah? But constant volume, delta U is equal to QV. And therefore, C, your heat capacity, becomes CV as QV over delta T. And we know that QV is delta U, so therefore CV is delta U over delta T. Okay, that's one way of calculating delta U. If you know you're working at constant volume, then your is going to be equal to CV times delta T. Yeah? However, in chemistry, yeah, good. It's unusual to work at constant volume. We normally work at constant pressure. Okay? Because if you think about doing a constant volume, that means putting it in a very, very rigid flask with a strong lid on top of it that's probably made in stainless steel and nothing can escape. No gas can escape. It's going to be constant volume. And that's not what we do in chemistry. We normally work in a beaker in an open environment. Yeah? In your beaker, because we work in the lab, you can assume that the atmospheric pressure is constant when you do your experiment. Yeah? So we normally work at constant pressure. So when the volume can change this time, your internal energy is not equal to the heat transfer, because we can make work. Yeah? And it's difficult to work out delta U when you make work, because working at work is difficult. We know that. We saw that earlier. Therefore, we need to define a new state function, and that state function is called enthalpy. And basically, it's called H, and H is the internal energy plus PV, which is your work. Okay. So PV takes account for work, and therefore we get H, which is our new state function. So delta H. So let's look at property. So that H is equal to U plus PV. Then change in enthalpy delta H is equal to delta U plus delta PV. Okay. That's equal to delta U plus P delta V plus V delta T. Just expand it, delta V. Now we know that delta U is Q plus W plus P delta V plus P delta V. Now we're working at constant pressure. What was the work for constant pressure? Work for at constant pressure, what was it? No. Minus.
Minus V.
Yeah. So that's Q minus P delta V plus P delta V plus V delta V. That cancels out. So therefore, delta H is Q plus V delta V. Yeah? And also, what I forgot to say is that working at constant pressure, so the change in pressure is zero. Delta P is zero. So that is zero. So therefore delta H is equal to Q.
This is constant.
This is equal to constant pressure. Yeah? And because it's constant pressure, we write it as QP. Which is what you have here. At constant pressure, delta H is equal to Q. So we can do the same thing as before with our heat capacity. So the heat capacity at constant pressure is equal to QT over delta T. That's delta H over delta T. Yeah? So remember, there are tables for the heat capacity. So we know that Cp, if we know the change in temperature, we can work out delta H. Okay? Now there's a relationship between Cp and Cv. Okay? So if you work at constant pressure, most systems will expand. You will emit some gas. Okay? So therefore they lose energy to the surroundings as work. The result is that the temperature of your system rises less than the same if the same process happened at constant volume. And that leads to the fact that Cp is always going to be greater than Cv. And the relationship between the two is that your Cp minus Cv is equal to n number of moles in your system times the gas constant. Okay? So therefore, tables are always reported as Cp. Okay? You will always find Cp because from Cp you can find Cv by applying this relationship. Okay. So you will never find tables of Cv, always find tables of Cv. So, that was a bit of thermodynamics, but realistically, what we do is thermochemistry, because we don't do thermophysics in this course. And because we want to study reactions and transformations in your system. So there are three important properties of enthalpy. Is that at constant pressure, the enthalpy is equal to Qp. The enthalpy is a state function as well. Okay, that's another important one. And your Cp is the rate of change of enthalpy with temperature. These are three very important things that we use in thermochemistry. So in practice. Now, standard states. A lot of the time, you're going to find things reported as delta H0 with a 0 like that, or 0 with a bar across. Okay? Yeah.
Isn't it the bar across was theta?
Means
Theta?
theta. No, it's just it's not just like that. It's you get that and cross like that. Okay. So you will find things reported like this, with a 0 like that or 0 crossed. Okay. That means it is reported in the standard state. That means the measurement has been done at 1 bar of pressure. Okay? And that's the definition of the standard state, is that the substance was at 1 bar. Okay? There's no temperature involved in there, in the standard state. The table will probably say the measurement was done at 25 degrees C, to 298 Kelvin. But that doesn't imply that if you change the temperature, you will remove the 0. Okay? The 0 only means that it's in at 1 bar. Okay. Now that's, you're going to say, is counterintuitive, because I've always told you use SI units. 1 bar is not an SI unit. Okay? But we know that SI unit for pressure is Pascal. However, in the past, people didn't work with SI units. Okay? So that's historical. 1 bar is the atmospheric pressure, basically. And that's why people have done that.
Is it easy to measure it at 1 bar? Is that where they use bar for the standard solution?
I think it's because in the past, they did not really measure the pressure. They said the atmospheric pressure is 1 bar, and it doesn't change. Okay.
So that was just randomly noting.
Yeah. Okay. However, we know that there are slight differences in the atmospheric pressure every day, but basically they just decided that 1 bar was their standard. Okay. And there are tables to convert bars to Pascal and backward as well. So standard states can be hypothetical. Sometimes you can get that substance at 1 bar, okay? But there is a number because it's been calculated, okay? It's not always achievable. So if we think about enthalpy for physical change, so we go from liquid to gas to solid. Each transition has a corresponding enthalpy. So you can get enthalpy of fusion, enthalpy of solidification, enthalpy of sublimation, and in general, you need energy to go from one to the other. Yeah, we know that. So for example, to go from ice to liquid water, the delta H fusion is 6.01 kilojoules per mole. Okay? Because enthalpy is a state function, it does not depend on the path, but on the two states. So therefore, if I wanted to work out delta H sublimation, I can do it as delta H of fusion plus delta H of vaporization. Yeah? So if I don't know that, but I know this one and this one, then I can work out that one. Because sublimation is gas to solid, so I can go that way and that way. Or that way, that way. Yeah? Remember, it's a state function. It only depends on the initial state and the final state, not the path. So that might be the fastest path, but I know this one and this one, so I can work out this one. Also, if you find that delta H from B to A in the table, then it will be minus delta H from A to B. Okay? So the same process in reverse has the same energy, but in a negative way. Okay? So for water, delta H vaporization at 273 Kelvin is 44 kilojoules. So delta H condensation is minus 44 kilojoules per mole. Okay. So therefore, in tables, you will always only find one change, because it's obvious that the other one is the minus. Okay. Yeah, so you only get vaporization from the fusion and sublimation in the tables. The reverse process, is the minus. So, how do we work out the enthalpy of a reaction? So, if we have our reaction here, what we want to know is how much energy is going to be released or absorbed when I do my reaction. It's not always E. Okay? So the thing to remember is that we have a step function. So to take a delta H for the reaction, R is because I'm doing the reaction. Then if we can break the reaction into several different reactions, that's going to be easy than working at the whole thing for the whole reaction. Okay? So Mr. Hess came up with this law. Hess's law. The standard enthalpy of a reaction is the sum of the enthalpies for the reaction of the reaction into which the reaction can be divided into. Okay? So if you can break your reaction into lots and lots of small ones that you know the enthalpy of, then you can work out the whole thing for the reaction. That's what we have here. You have your initial stage and your final stage. That's my reaction. I can break it into two different ones. That's going to give me the same result. So for example, I'm taking nitrogen gas and I add oxygen to it to make NO2. I can break that into two small steps. I can make N2 plus O2 to give 2NO. I know that's 100 kilojoules. I can take my 2NO, add O2 to it to make 2NO2. If I add these two together, the NO cancels out. I get N2 plus 2O2 is 2NO2, which is that. I know the delta H for this reaction, so I can add them together and I get 68 kilojoules. Yeah? So if you know the delta H of several reactions that give us that we can break our reaction into, then it's going to happen. And that's his law. So for chemical process, generally, delta H0, if you want, for the reaction, is going to be the sum of the H for the product minus the sum of the H for the reactant. Mu here is your stoichiometric coefficient. Okay? So therefore, if you take this reaction here, the delta H of the reaction is going to be H0 for CO2 plus 2 H0 for H2O minus H for CH4 minus 2H for O2. Yeah? Now the problem is, do you remember that H is U plus PV? Yeah? We don't know how to work out U, because it's the sum of all the energies of all the atoms, all the bonds, everything. So therefore, we don't know how to work out H. That's the problem. Okay? Therefore, what we have worked out, what people have worked out, is the enthalpies of formation, delta H formation of a substance. Okay? So delta H of formation of a substance is the standard enthalpy per mole for the formation of a substance from its elements in their reference state. Okay? If you want to form an element, then, for example, if you want to form O2 or H2 or that kind of substance, the delta H formation is going to be 0 always. So therefore, my delta H reaction now is going to be the sum of the delta H formation of the products minus the sum of the delta H formation of the reactants. Okay, so if we take that example here, what we have can just memorize that thing here. I can write it as, I'm going to start with carbon, oxygen, hydrogen. I'm going to form CH4, I'm going to form O2, I'm going to form CO2, I'm going to form H2O. Yeah? So I'm going to get delta H formation of CH4, 2 delta H formation O2, delta H formation for CO2, and delta H formation 2 delta H formation for H2O. Yeah? Remember, it doesn't depend on the path you take. Therefore, I can take these, put them into the elements, then take these, and then form these two. Yeah? If my total arrow here goes against those arrows, it's going to be a minus. If I go in the same direction, it's going to be a plus. So deform CH4 and deform O2, so it will be minus that, and forming CO2 and forming H2, so plus that, plus that.
So the beginning is always minus?
If your arrow, which goes in that direction, is in the opposite direction, it's going to be a minus. If it's in the same direction, it's going to be a plus. Okay. So I'm going from there all the way to there. Yeah? So I'm going in this direction, downwards. So I'm going against the formation. That's one thing. Yeah? Does that make sense? Or you can just remember that it's the sum of the products minus the sum of the reactants. It's up to you. Okay? And remember, the transformation of an element, O2, it will be 0. So that one's going to be easier already. So I guess the transformations are reported in tables again, so that's easy. Just have to find them, and then I put them there. I put the answer there. You can try to do it at home. Okay. See if you get the same one. So does enthalpy depend on temperature? If I do it at a different temperature, am I going to get a different amount of energy? So most of the time, the enthalpy is not evaluated at the temperature you want. Okay? So therefore, we need to know our enthalpy change with temperature. And we know that delta H is equal to Cp delta T. We saw that earlier. So if heat capacity is independent of temperature, we saw that as well, then we know that the initial enthalpy at some initial temperature T1 and then the enthalpy at different T2 is given by that. So you're going to get what we call Kirchhoff's law. You can change delta H. You can work out delta H of the reaction at T2 is with delta H of the reaction at T1, and you're going to get delta Cp T2 minus T1. Okay? So delta Cp is the difference of the Cp of the products minus Cp of the reactions. The good thing is that has virtually no effect, because delta H is now in kilojoules per mole, and Cp is in joules per mole. So delta H is 1,000 times bigger than delta Cp. Yeah? Therefore, the change of temperature, the change in temperature on enthalpy is very small. Okay? So most of the time you can assume that delta H is constant within the range of temperature we study. Most of the time. Okay. Have a break.
Yeah.
This second one is already really hard for me.
Okay. Have you got any questions on the first law, on entropy, or what we saw so far? Yeah.
Are there examples of like naturally occurring isolated systems eventually limited?
Not naturally occurring?
Isolated systems?
Can you say it again?
Naturally occurring isolated systems.
Well, is that universe? Oh, right.
You could say a pea in a freezer.
That isn't naturally.
It's difficult to find an isolated system actually. From the top of my head, apart from the thermos flask, something in the freezer.
But are they truly isolated, or is there going to be some around it?
Being completely isolated is very, very difficult. Very difficult. Because remember,
That's homework.
oh,
That's
thank
my
you.
homework.
Yeah. It's because you don't want any exchange in energy at all, and any exchange of mass. So therefore, it is always very difficult to achieve. Always.
When we study the law of conservation of energy, we only talk about the universe. We don't apply that to
Generally, yeah. Okay. As I said, universe is one I know. After that, it always depends on how you define your system, but yeah, it's a truly isolated system is very difficult to find. Very. Okay. Any other questions? Everybody happy? Then we carry on. Okay. So the first law explains where the energy goes, where it comes from, but it has limitations. And the limitations is that it doesn't tell us what happens to energy afterwards. Because there's going to be friction, there's going to be loss of energy, your energy can dissipate through heat, and it disappears. And the first law does not explain that. Therefore, people needed a second law, thermodynamics. And first of all, we talk about spontaneity. So if you imagine you have a gas here and a vacuum here, and then there's a tap. When I turn my tap, what happens is that my gas molecules go spontaneously into the other side. I'm not forcing them, I'm not putting any work into it, and also we know that if you expand into a vacuum, there's no work done. Okay? And because it's all isolated, then there's not going to be a change of heat. So therefore, there must be a driving force that forces all those molecules to spread out. Same thing if I take temperature. So I have two blocks, one at temperature A and one at temperature B. And temperature A is greater than temperature B. We know that the temperature of B is going to increase until they both have the same temperature. Therefore, heat moves from A to B. Not forcing them, not doing any work at all. It just happens. So all this process tends to be spontaneous and no work is required. Okay? So remember, the thing is that thermodynamics will tell you whether it's going to happen or not, but it's not going to tell you how long it's going to take. Okay. So spontaneous reaction. That is your nice room at the beginning of term. After 3 months, that's probably your room. Yeah? It happens spontaneously. But if you want to do it, to go back to that, you have to put work into it. That's, in that direction, that's not spontaneous. Yeah? You do no work, that goes there. You do work, it goes back to nice and tight. That's what spontaneity is. So the driving force for spontaneous change is what we call entropy. Okay? And basically, there's a tendency for matter and energy to go towards disorder. So what happens is that your system has lost some capacity for carrying out work. Remember, work is a nice, orderly, motioned force. Yeah? If you go into messiness, it's not going to be ordered. Therefore, you cannot do the work anymore, because the energy is very random. Okay? So, for example, if we take the gas that was expanding into the vacuum, what we could have done is we could have plugged it into a turbine and make electricity from that. But as soon as it's gone to the other side, that's it. You cannot do it anymore. Yeah? So your system loses energy to do work. As said, the driving force is called entropy, and we write entropy as S. So the second law of thermodynamics says that for spontaneous change, the entropy of the universe has to increase. So delta S universe has to be greater or equal to 0. And remember, delta S universe is delta S system plus delta S surroundings. So for something to happen spontaneously without putting any work, the delta S of the universe has to increase. You must increase the randomness in the universe. Okay? That's the law of thermodynamics. So, how people have defined that law? So generally, heat cannot flow from a material at a lower temperature to a material at higher temperature. We saw that earlier with the 2 blocks. Yeah? The heat goes from the block at higher temperature to the block at lower temperature. Heat goes from higher to lower temperature, always. What does that mean when you put an ice cube in your glass? It's the other way around. Heat always goes from higher temperature to lower temperature. Therefore, you put an ice cube in your glass to melt your ice cube, not to cool down your drink. Okay? When you put an ice cube in your glass, you melt the ice cube. You're not cooling down your drink. In the process, your drink cools down because heat leaves the drink to go into the ice cube to melt it. Okay? It's impossible to convert heat completely into work. That's what Lord Kelvin said. That's the same thing again. You lose some kind of energy into the system, into the universe. And then there's my take on the angry cat. So remember my angry cat. That's the energy in the room that's closed, and that's all my chemical reactions there. I'm going to leave my angry cat a bit longer in the room, and it's going to find one of those jigsaw pieces, and it's going to start to chew on it. Yeah? And that piece, once it's chewed, I can't see the picture anymore on it, I can't use it anymore. So that energy is lost. It's there, but I cannot do anything with it. And that's the second law of thermodynamics. So how do we work out the entropy? So that's one formula we can use. And S is the entropy. Kb is what we call Boltzmann's constant. We got a log, and we got omega, which is the number of ways of arranging the molecules in your system. So if you have a large number of arrangements, if you have a large number of omega, S is large. If you have a low number of omega, S is small. So how does that work? Think of a gas. I get lots and lots and lots of ways I can arrange my molecules in the gas, in my container. Therefore, my omega is high, so S is high. So I get high entropy for a gas. In the solids, there's probably just one way I can pack all my molecules together. Yeah? So there's a low number of arrangements. Maybe I can move a little bit there, a little bit higher there, but not much. Okay? Because everything is fixed in the solid. So omega is low. That's a low number of arrangements. So I get a low entropy. So gas will always have higher entropy than a solid. That's why people say that the entropy is a measure of disorder. Yeah? You can think that that is very disordered from that. Because that's going to be fixed, and that's going to be completely wrapped up in my whole container. Now the problem is that there's no way we can work out the number of arrangements in our system. You know, I'm not going to sit here, look at my gas, and think, yeah, that molecule can go there and there and there and there, and then the second one can go there and there and there and there, and count all the arrangements. That's not practical. Okay, so we need to find a way of defining entropy through heat. So ds or delta S is written like that. So ds. So a small change in entropy is a small change in reversible heat divided by the temperature, or delta S is the heat, reversible heat divided by the temperature. Okay? So the units of delta S are joules per Kelvin or joules per Kelvin per mole. That is the formula I want you to remember. Delta S is Q over T. The nice thing is that entropy is also a state function. What does state function mean? Yeah, so it depends on the initial and final state, independent of the path it takes. So how does entropy change with temperature? So we know that ds is dq over T. And delta S is going to be S at temperature 2 minus S at temperature 1. And therefore we're going to have to do the integral again. That's dq over T. Okay? And dq over T is C dt. Yeah, remember Q is C delta T, therefore dq is C dt. We saw that in the first part of the lecture. So we put that in there. So we're going to get C dt over t. I have here C dt over t. And C, we said that doesn't really depend on temperature, so that's good, so we can take it out, and we got dt divided by t. Remember what we did earlier? What was dv over v? What's the integral of that? Remember? Log of v, same thing. So that's dt over t must be log of t. So we're going to get the same thing. So delta S is the heat capacity multiplied by the log of T2 over T1. With T2 is the final temperature and T1 the initial temperature. Okay? And that is for reversible process. Has to be reversible. So if you think about phase transitions, okay? So at the melting point or the boiling point, you get transfer of heat reversibly. So what it means is that if you have your system at melting point, you can input a little bit of heat in there, and your system is going to melt. If you're just above the melting point, you can get rid of a little bit of heat, and it's going to solidify. Okay? So that's it there. So this time, you get temperature that's constant, pressure and volume are constant as well. So we know that Qp is equal to delta H, and then so we find that the delta S for fusion or delta S vaporization is equal to delta H fusion at the fusion temperature divided by the fusion temperature, because that's where your system is at. Same thing for delta S of vaporization. Okay? So that's quite two important results, that delta S fusion and delta S vaporization are equal to the enthalpy divided by the temperature. Okay? That's one way we can work out delta S. Now we said that to work out whether the system is spontaneous, the delta S of the whole universe has to increase. Now, all we did up to now is calculate the entropy of the system. We haven't touched the surroundings yet. So the surroundings is a big reservoir, and we can normally say it's a constant volume. Okay? It's everything around our system, so we can say the volume is constant. And the energy supplied to them can be in terms of the change of the energy of the surroundings. So du surroundings is independent of the energy, how the energy is brought in the process, and it's independent whether it's reversible or not. It doesn't matter. Remember, delta U is blind. And we know that du of surroundings is dq of surroundings. Yes, a constant volume, U is equal to Q. Remember that? Okay. So therefore, dq has the same properties as du. dq surroundings is also a state function. So therefore, my delta S surroundings is going to equal to Q surroundings divided by temperature of the surroundings. And that is regardless whether the system is reversible or not. So for the system, delta S has to be reversible. The system has to be reversible to calculate delta S. For the surrounding, it doesn't matter. So how can we work out S as a predictive tool? So we know that if delta S of the universe is greater than 0, then my process is going to be spontaneous. If delta S of the universe is less than 0, then the reverse process is spontaneous. Yeah? So if I work out that delta S of the universe for that fraction is negative. That means that fraction is spontaneous and that one is not. Okay? And if the delta S is 0, that's what we call the equilibrium conditions. So we are in equilibrium. We get both things happening at the same time. Go on.
So if the process is continuous, it means that it goes forward time?
Yeah, forward direction.
And then I can say that the backward, the reverse reaction is always unspontaneous.
Is it always?
It's unspontaneous? The
Yeah,
forward reaction?
it's non-spontaneous, yes. Unless delta S is negative. Then it's the other way around. Okay? So equilibrium. If A is in equilibrium with B, and if B is in equilibrium with C, then C must be in equilibrium with A. Yeah? That's what we call the zero flow of thermodynamics. Or as I call it, the law of pretty obvious. Yeah? Makes sense. That's another law. 3 laws so far. It's exciting. So, if you take a temperature of 0 Kelvin, that is not achievable. No one has ever been at 0 Kelvin. Okay. The best people have done in the lab is 10 to minus 4, 10 to minus 5 Kelvin, but not 0. Okay. The coldest point in the universe is 0.01 Kelvin in space. Okay. But if you manage to reach 0 Kelvin, at that point, everything is going to stop. Everything is going to be fixed. There's not going to be any vibration, and you will get a perfect crystal with no default, nothing. At 0 Kelvin, everything is perfect, everything is fixed. Okay? Therefore, there's only going to be one arrangement. Only one possible. If there's one arrangement, the log of 1 is always 0. So therefore, the entropy at 0 Kelvin is 0. Okay? So you have here, omega is 1, and therefore S is going to be 0. And that is the third law of thermodynamics. The entropy of all perfect substance, crystalline substance is as 0 at 0 Kelvin. And that is quite useful. No. So therefore, we just assume. Okay? Like with every law in thermodynamics, there are postulates. Therefore, we're assuming they are true. If you can prove they're not true, you'll get the Nobel Prize. Okay? Because you've changed the whole way that we're going to think about chemistry. Okay? But so far, no one has been able to prove they are not true. So we still assume they are true. That's the way it works, always. Okay? So, the second law is always going to tell us how to predict whether a process is going to occur spontaneously or not. We can work out delta S universe, and if it's greater than 0, or if it's at equilibrium, it's 0. Okay? However, the second law is not very convenient to use, because we need to work out delta S of the system, delta S of the surroundings, add them together, and work out delta S of the universe. And working out delta S surroundings is always difficult. Okay? Always a pain. So, as I said, it's very tiresome. There's some people don't want tiresome things, you know. We are scientists, we are lazy. We want to work out shortcuts, always. Therefore, people have devised a new state function. And the new state function is called Gibbs free energy, and it's called delta G. And delta G is defined as delta H minus T delta S. So it's delta H from the system and delta S of the system as well. Okay. So delta G, if that delta G is negative, then the process is going to be spontaneous. If delta G is positive, then it's the reverse of spontaneous. If delta G is 0, we are at the equilibrium. Okay? So that you have to be careful with, because that's the reverse of delta S. Remember, delta S has to be positive to be spontaneous, but delta G has to be negative. That is because we put a minus in front of delta S here. Okay? So my Gibbs free energy is the heat that goes into the system minus the energy that's wasted. Okay? So what's happening? If delta H is negative, so that what does the negative delta H mean? If it's negative, what does it mean? No, that means that heat is leaving my system. Yeah? If delta H is negative, that means that the heat is leaving the system. Negative is leaving the system. And delta S is greater than 0. What does delta S greater than 0 mean? No? What is delta S? Entropy. What do we say that delta S represented?
Disorder.
The disorder. So if delta S is increasing, what else is increasing? The disorder in my system is increasing. Yeah? So if heat is leaving my system and I increase the disorder, then my delta G is always going to be negative. So the reaction is going to be spontaneous.
The what?
The reaction will be spontaneous. Okay? Now work out all the different cases there. Okay? So you can get delta H greater than 0 and delta S negative. But it's not always spontaneous. It depends on the temperature and so on and so forth. Sorry. Okay? So what you have to keep in mind is that when you do your calculation of delta S on your system, you cannot make any prediction at all. All you can say is if delta S is greater than 0 for the system, that the disorder is increasing. So you can go from a solid to a gas, for example, that's increasing disorder. But you cannot tell whether the reaction is spontaneous or not. You can only do it if you work out delta S of the universe or if you work out delta G. Just doing calculations on delta S of the system will only tell you whether the messiness, the randomness of the system is increasing. That's all you can say. Okay? So because both enthalpy and entropy are state functions, then my Gibbs energy is going to be a state function as well. Okay? And that's useful again. So I'm going to get that delta G0 for the reaction is going to be delta G0 of the products, which are like the Stochastic coefficient minus that of the reactants. Okay? So we can use the same formula as Hess's law. So we also see that we can get delta G0 and delta G0 for formation. So the same way as delta H was worked out for formation of different elements or different compounds, we have the same thing for the Gibbs free energy. Okay? So the Gibbs free energy of formation is defined as the change in free energy that changes one mole of substance from its constituent elements, and all the reactants and products are in the standard state. That's delta 0 there. What's the standard state again? What was the standard state?
When the is independent.
Yeah, but
Doesn't matter. Only the initial are known.
no, that's not the standard state.
Pure substance.
At
1 bar.
1 bar. Okay. And same thing as before, that delta G0 formation of an element in its standard state is going to be 0. Okay. So delta G works exactly the same way as delta H. If you can do calculations on delta H, you can do the same thing on delta G. It's the same one. And as such, Hess's law can be applied to delta G. So if you do this one here, what happens? The question is our diamonds spontaneously going to graphite? What do you think? Who thinks yes? So everybody thinks no. Diamonds do not go into graphite. Yeah? Okay, let's work it out. Okay, so I'll remember the numbers. So I know that if I add O2 to diamond, I create CO2. And same thing if I add O2 to graphite, I'm going to make CO2 as well. Yeah? And from there, I know that delta G0 for diamond, so delta G0 for this reaction is minus 397 kilojoules per mole. And that one is minus 394 kilojoules per mole. So we said we could use Hess's law. Yeah? So I can go, instead of going that way, I can go this way. Like that. So what's going to be delta G0 here? So what do I put first?
And we put that minus 394 plus.
Yeah. So I'm going in the same direction here. Yeah. So therefore it's going to be that number. So minus 397. I'm going against the arrow here. So it will be minus 394. What can you see?
But isn't it the products minus the reactants? Would it be like the opposite?
Why?
Because I don't know, the formula is
Do we know G0 for that? No. We know G0 for this fraction. Yeah? And we know delta G0 for this fraction. Therefore, we need to create a cycle. Okay. Remember? We need to break it into reactions we know. Yeah? So, if we wrote it this way, okay. C D for diamond plus O2 gives CO2. Yeah? And C graphite plus O2 gives CO2. Yeah? If I want to make this reaction here, I have to do C that one minus this one. I do minus that one, I flip it. Yeah? So therefore, it's going to be that one minus that one.
Why do you see you've said that? Because
Doing minus that is the same as doing that, or plus CO2 into C plus CO2. Yeah? Same as splitting direction. I, personally, and it's up to you how you do it, prefer to draw it like that, because to me it's more intuitive to write it as directions and then follow the arrow. Okay? What you do is your business. Okay? I find it easier to see it with a graph. But that's me. Okay? So therefore, I'm going to do this one minus this one, so that's 397 minus 394. So plus 394. That's going to be minus 3. Delta T0, negative. What does that mean? Diamonds spontaneously transform into graphite. Yeah? What did we say? Things tend to go to this order. Diamond is very nicely ordered structure. Graphite is more messy. It will go towards this order.
Can you also calculate how long it will take?
Exactly. Okay? Thermodynamics tells us whether it's going to happen or not. Kinetics will tell us how long it's going to take. Okay? Kinetics will tell us that's going to take millions of years. Okay? But it will happen. So when Shirley Bassey sings Diamonds Are Forever, she's a liar. They are not forever. They might be forever in your lifetime, but in the lifetime of the universe, they are not forever. Sorry? So the kinetics will tell us how long it lasts. Okay? As I said, it takes millions of years. So that's exactly what we did. Yeah. So what does G really mean? So if we take this one, for example, on one side I got 100% reactants, and on the other side I got 100% products. If the Gibbs energy of my reactants is higher than the Gibbs energy of my products, delta G is going to be G of the products minus G of the reactants. Yeah? It's always the same for delta. Therefore, I'm going to get a negative delta G, so that's a smaller number minus a larger number. And you can see, sliding down. That's going to be spontaneous, because the energy of the products is higher than the energy of the energy of the reactants is higher than the energy of the products. The system will always want to go towards lower energy. Okay? But low energy is more stable, always. The other way around. My reactants have a smaller energy than my products. So therefore, products minus reactants, I got a large number minus a small number. Delta G is going to be positive. It's harder to go up the curve. Yeah? You need to put lots of work to counteract that. Therefore, it's not spontaneous. You need to put work in to happen. And then we're going to get things in the middle, when your products and your reactants roughly have the same energy. And we come into what we call an equilibrium. Okay? And the equilibrium, E there, is going to tell us whether, depending on where it is going to tell us that at the end of the reaction, I'm going to get a pot with maybe, let's say, 66% reactant, 33% products. Yeah? That's what it means. The reaction will not go to completion, yeah? But I'm going to get a mix of both, of reactants and products. Now in chemistry, 99% of reactions are equilibrium. Okay? You will always get that molecule, that stupid, ridiculous molecule, that has enough energy to go back up. Okay? And that means that you might, people say, oh yes, it's spontaneous, 100% theoretical yield. Yeah? But it never happens because it's always going to be 99.99 somewhere there. Okay? It's never going to be 100% theoretical yield. Okay? Now Gibbs free energy, what it really is. So I've got heat that's coming into the system or leaving the system, and wasted energy from delta S. So remember the formula for Gibbs free energy is delta H minus T delta S. Yeah? So delta H is the energy of my system, minus T delta S, which is the energy wasted by the system. So that's where Gibbs free energy comes from, is the energy that is free for the system to use. It's the energy minus the wasted one. And that's the energy that's left into your system for it to use to carry on working. That's all it means. Okay? Are there any questions? Yeah?
In the equation, if S is equal to KB log
Omega?
omega,
Yeah.
is that for an isolated system?
Is that what, sorry?
That this is for an isolated system?
Yeah.
Equation. So can you calculate it for the entropy?
As I said, it's very difficult because knowing omega is a difficult thing.
But can you say from this equation if the entropy is omega is which
No, people don't use that formula to work out. It's just that the way it was devised to start with, okay, is to explain the disorder thing. Okay? Is to put some mathematical meaning into the disorder. Okay? But people don't use it to calculate the entropy of the universe. So you use delta S equals Q over T. Yeah? So you use delta S equals Q over T for the system and for the surroundings. And you add them together to get the universe. Depends. If your reaction is spontaneous, yes, the entropy of the universe has to increase. If they are spontaneous, if all the reactions in the universe were spontaneous, the entropy of the universe increases. In general, yes. Yeah? In general, if you add everything together that's happening in the universe, the delta S in the universe increases. And that's the reason why we die. Okay? Our system, our body, all the reactions tend to be spontaneous, and we tend to go towards disorder. And disorder is the death of your cells. So entropy kills us. Okay? Now before you go, I want to do a little exercise.
Sorry, should
Yeah.
we be able to manipulate all those equations with
Yes. before you go, I want you to tell me what you have learned today. So you do the summary of what we did today. We've seen lots of things today.
Oh, different kind of systems.
Systems, yeah. Spontaneity.
Spontaneity doesn't require energy.
Yeah.
Work and heat.
Work and heat. Remember the formula for work? Okay. What was the formula for heat? Yeah. C delta T. Yeah. Good. Anything else? What else do you see? The SI units. Yeah. Joule or joules per mole. Interenergy. And we said that delta U is equal to Q plus W. Yeah. Sorry? Enthalpy is equal to, and delta H at constant pressure is QP at constant pressure. That's the important one to remember. What else do you think?
State functions.
The functions? What's the step function?
State function is the value, the value is the initial and the
Step function only depends on initial and final states, not the path taken in between. Yeah? Come on, we saw lots more.
standard states.
Sorry?
Standard states.
Standard states. What's the standard state? Pure substance at 1 bar. Yeah. That's written noted as 0 or 0 bar. Yeah. Sorry? The?
There is no temperature.
Yeah. Correct. There's no temperature in the standard state.
Entropy.
Entropy. What do we know about entropy? What is it? Sorry? It's going to kill us? Yes, yes, entropy will kill us. It's a measure of disorder. Yeah. What else do we know about entropy? What was the second law of thermodynamics?
Spontaneous change the entropy of the
So delta S anywhere has to be greater or equal to 0 for spontaneous change. Yeah? So that is the second law of thermodynamics. What was the first law? Yeah, the energy of an ICT system is constant, and also we can write it as delta U equals Q plus W as your first law of thermodynamics. What is the third law of thermodynamics?
And 0 Kelvin, the entropy is 0.
Yeah. S equals 0 at 0 Kelvin. Choose okay, sorry. What else did we talk about?
Gives free energy.
Gibbs energy, yeah. So what's the formula for Gibbs energy? One to remember. Okay. So if I calculate delta S of my system, can I make any prediction?
Well, you can just say if it's going to be more
Disordered.
disordered
More or less.
yeah.
Yeah,
But you can
So you-
otherwise we need delta G to predict.
correct. Okay. So if you only work on your system, you can only make prediction with delta G. Delta S will only tell you whether it's going to be more or less disordered. Okay? Happy? No, yes, maybe, I don't know. There's lots and lots to digest. Okay? When people study thermodynamics for the first time, they don't understand it. When you study thermodynamics for the second time, they think they understand it. When you study thermodynamics for the third time, you definitely don't understand it. Okay? So I know it's your first time. Okay, so I know that. So I know there's lots of information to take in. Okay? But if you follow the rules I've given you, you should be able to make predictions. Okay?
But that's what we do, make predictions or also calculations?
You make a prediction by doing calculation. Okay? Alright? See you later.